This is the solution to problem number 3. All right, so here's the problem. We had a review problem for free body diagrams. You should have already solved this by now, but let's go through the solution. Here's my strategy. I need to find the tension. That's all I got to do is find the tension. So my strategy is real simple. I'm going to sum up the forces to find the tension because I'm looking for a force. All right, that's easy enough. Now let's start with the free body diagram. So let's look at the car. The free body diagram of the car, it's a 10-degree slope. And there's my little body. It's just the dot, not drawing the car. And it's got the car is exerting a force up the incline. So there's my force of the car. And it's got a rope pulling it backwards along the incline, parallel to the incline. So that's my tension. It's on the earth, so it's going to have weight going down. So I'll label that as mg going down. And because there's a surface, hard surface there, it's going to be a normal force that keeps the car from sinking into the surface. And the normal force is perpendicular to the surface itself. So there's my eta, which is normal to the surface. So great. Now I need my second free body diagram. For my second free body diagram, I'll start with the angle, and there's my body right there. And I'll repeat everything I have on the first one, but this one's going to have components to it. So the normal force, the force the car exerts, and tension are all perpendicular to each other. To create the components, I'll make sure they're parallel and perpendicular to the incline as well. Perpendicular to the incline and parallel to the incline. Remember, the angle at the top of the triangle is the same as the angle at the corner, right-hand corner of the incline. So it's 10 degrees. The component of the weight that is perpendicular to the incline is mg cosine 10. It's adjacent to the angle at the top of the triangle, and at the bottom, that's going to be mg sine 20, or sine 10 degrees, sorry. All right, time to sum up the forces. So I'm going to sum up the forces parallel and perpendicular to the incline, since that's where most of my forces are located. And this car is moving up the incline at a constant velocity. So when I sum up the forces in the y direction, it's equal to 0 because it's not accelerating up and down perpendicular to the incline. So 0 is equal to normal force minus mg cosine 10. And then I'll sum up the forces in the x direction, that's along the incline itself. And this is also going to be equal to 0 because it's not accelerating along the incline. It's moving at a constant velocity, so its velocity is not changing. So since its velocity is not changing, sum of the force is going to be equal to 0. So 0 is equal to F minus mass, the car times g, sine 10, minus the tension. Remember, with assigning directions, everything going one direction is positive, everything going the opposite direction is negative. That's why F is positive, and negative 10 mg sine 10 and negative t are negative signs. I hope that makes sense. All right, so I'll write this expression as 0 is equal to F times mg sine 10 minus tension. Isolate tension. And I realized, oh, I don't need a second free body diagram to answer the question. I was thinking I would have to draw one for the box too, but to answer this question, I don't. And that's because they gave me the mass of the car. So that's easy enough. I got tension, I got force minus mg sine 10. So tension is equal to 4,000 newtons minus 1,100 kilograms times 9.8 sine 10. And that gives me the tension of the rope between the box and the car of 2,130 newtons. In case you're wondering, if I was to draw a second free body diagram for the box that's being towed, it would actually look something like this. But as it turns out, I don't need that because I had enough givens where that wasn't necessary.